Okay, we're going to talk about acid-base dissociation constants. Dissociation constants. Okay, and for an acid that would be a Ka, for a base it would be a Kb. It always helps me to first write the reaction. If we take HA as a weak acid in solution, and it's in water, that sets up an equilibrium with the anion and the hydronium ion. Right, your Ka then is your anion times your hydronium, and that would be over your weak acid concentration. Remember that water is a pure substance, so it doesn't enter in. Let's look at a real quick problem using a dissociation constant. If you are given a Ka and asked to find the pH, well, if you're given the Ka, oh geez, hang on. Say the Ka is equal to 1.8 times 10 to the negative fifth at 298 K, and you know you have a 1 molar solution of acetic acid, that is C3COOH, okay, and you're asked to find the pH. In solving this problem, I would first write the equation for the dissociation of the acid. You have the anion and then the hydronium ion. I'm dropping the state symbols. We need to set up an ice table. Anytime you're given the concentration of the acid, that is the initial condition for the acid. Water doesn't enter in. You assume that it is not dissociated or ionized in the beginning. Hopefully you can see that the equilibrium is going to shift to the product side. 0.1 minus x, x, and x. We're going to assume that x is much smaller than 0.1. Your Ka, you know the expression from before, that's 1.8 times 10 to the negative fifth. That's equal to x squared over 1.8 times 10 to the negative fifth. Solving for x, x is then equal to 1.34 times 10 to the negative third. That is less than 5% of your 0.1, so you're okay. The pH is then equal to the negative log of the concentration of hydronium, which is x. Putting that in the calculator, you should get 2.87. Okay, the other type of problem is sometimes in your given, you will have, say, the concentration of the acid, and you are given a pH. This pH is going to be related to your hydronium ion at equilibrium. Okay. All right. There is something called Ostwald's Dilution Law. And this simply states that as a solution becomes more dilute, a weak electrolyte will become more dissociated. Or ionized. Okay. All right, moving on to something that is sometimes confusing. Hydrolysis, salt hydrolysis. Okay, really, what do ionic compounds do in solution? Right, so salts are ionic compounds, and you assume that they are going to become dissociated or ionized in water. And dissociated is actually the correct term. Dissociated in water. All right. Strong electrolytes completely dissociate. All right. If we look at an example, we have sodium chloride. When I put that into water, I form the sodium ion and the chloride ion. What we have to do is look at what are these things going to do in solution. Well, theoretically, if I have a sodium ion and water, remember we can think of water as being an HOH. What part of that water molecule is that sodium going to be attracted to? Well, it's a positive, so it's going to be attracted to the hydroxide, and I'd be left with the hydronium. You should remember that this is a strong base, so it remains completely dissociated, so there is no effect. It doesn't form because it completely dissociates, so the sodium ion will have no effect on the pH of a solution. Similarly, the chloride ion in water is theoretically going to make hydrochloric and a hydroxide ion. However, and again you need to memorize the strong acids and bases, this is a strong acid, so it will not affect the pH because it will remain dissociated. Now let's look at something that's actually going to affect the pH. Okay, say I have sodium acetate in water. This will form the sodium ion, which we just explained does not affect the pH, and then I will have the acetate ion. Well, this acetate ion in solution, again, remember, thinking of water as an HOH, would form acetic acid and a hydroxide ion. This is a weak acid, so there will be an equilibrium set up. When this equilibrium is set up, I'm going to liberate hydroxide ions. This solution will be basic. It's kind of weird because it makes a acid, weak acid, but the solution ends up being basic. Sorry. All right, let's take a quick look at ammonia and the chloride, ammonium chloride. This, again, this would form is the anion of a strong acid, so it's going to stay as a spectator ion. This NH4 plus with water is going to form, actually this one's a little weird, which is why I wanted to do this. It actually donates its hydronium, or its H, to the water molecule to form an acidic solution. Right, and this is one reaction that you should be familiar with, this equilibrium, and it really is an equilibrium of ammonium hydroxide with ammonia and the hydronium. If it was the other way around, you would have the ammonia plus water setting up an equilibrium with the NH4 plus and the hydroxide. And that's kind of the difference between the Ka and the Kb. I did that in class, and I'll probably make a screencast just to make sure that it's there for your reference. Okay, so the acidity of salts also depends on the size and the charge of the cation. And this goes back to the periodicity chapter where we had that aluminum chloride. Aluminum chloride as a solid, when I put it in water, is going to form, really, if you remember, it forms this complex ion and chloride ions. Again, chlorides aren't going to do anything in water, all right? But what we have to remember is this complex ion is then going to set up an equilibrium where one of the waters dissociates into this complex and then liberating, sorry, sorry about that, hydronium ion, so this ends up being acidic. And there's actually, it keeps going for a couple of steps. Okay, so hopefully that's clear. You will get a similar reaction with iron +3 and magnesium.